So yeah, thanks everyone. Thanks Cindy for the intro and everyone else for joining us at this last talk from the complex team this year. So this talk is on data storage and file systems, and I'll give you a little bit of an overview of today's webinar in a second. But if you haven't joined us in the past for complex, I did want to just sort of highlight sort of what the goal of the complex program is to new attendees. And so this is a training program we started early last year. It's funded by NSF, and the idea is really to try to develop a set of training material and exercises over the next few years to help end users of the supercomputers and HPC high performance computing resources, NSF funds, for doing their science, but may not be sort of, traditional sort of developers of a code. They might just be end users of a third-party code developed by a different research group to, get their science done. And so we're trying to come up with this collection of topics and material that will sort of help facilitate you in your work when you're working on these types of systems. So that's sort of the goal. And so today's talk is sort of, the second part, at least the second talk, I guess, I've developed as part of what I'm sort of focusing on in this data management training series. The last one, which is linked here, was the data transfer talk. Both of these are sort of new talks from, sort of refactoring and rethinking the material that we have had at SDSC for a while, but sort of fitting it, making it a better fit for the complex program. And so we'll see how it goes today. This is my first draft of this data storage and file system one, and the goal is really to teach you what a file system is. And so yeah, these are sort of the learning goals for today. Sort of, oops, lost my mouse here for a second on my side. My meeting, the chat window, sorry, blew up on me here. So I can't actually see my slides. Okay, there we go. So the learning goals for today are really to, teach you what, the concept of what a file system is and why, what some of the most common file systems you'll find on high performance computing systems like we have at SDSC, and how you will choose the different ones that might be available to you on any system. But the key thing that I think hopefully there's an aha moment at some point today is understanding the role of metadata and how that is sort of the key issue for understanding how to use different file systems and when, with whatever type of code you're running or data sets you're using, and sort of how you're packaging that data. It really is the key issue that most people don't understand, like why this is important. So sort of what I've been focusing on for this talk. So hopefully we'll get there and it'll make some sense. But yeah, we'll see how it goes. Please, and of course, since this is a new talk, please do fill out the survey if you can, and provide any feedback of things you would like to see. Again, so as part of this data management series, right? Data management is a very huge topic. I've linked here this nice link to the Harvard Biomedical Data Management sort of group. They have tons of resources there. But the things that we're focusing on complex is sort of in that core box, or the core circle of just how do you sort of move your data around and manage it on sort of the very sort of command line level that you have access to on these HPC resources. And of course, I put in the prerequisites, you need to understand a little bit about Linux and using sort of the command line tools that you use to navigate around, because at the end of the day, high performance computing systems run on Linux. And so that's sort of what we're assuming you have some base level knowledge of. But if you're like a Windows user and you've not sort of played around with sort of command line Linux a lot, I always like to put this recommendation out there to check out the Windows subsystem for Linux. You can kind of practice a bit more there, whereas Mac users sort of have access to a very Linux or Unix like operating system already. Okay. And as we get going, if there are questions, please feel free to put them in the chat, and maybe we'll stop at certain points and answer those questions as needed. And I'll try to keep an eye on the chat. But yeah, so this is sort of the table of contents today. The first goal is to really try to explain what a file system is. Might go into some detail a little bit about the different types of physical sort of storage devices and systems that these file systems live on. Then the key, hopefully, aha moment will be in this sort of files, directories, and inodes section, where we sort of bring together how these file systems are organized, regardless of what type they are usually that you're going to use, and sort of talk about some examples of the file systems we have here at SDSC, and sort of show you an example about performance and why all these other things and terminology that I teach you is important. And sort of we'll end with a quick list of sort of best practices that hopefully will make sense once you have some of these new concepts maybe that you haven't learned before. Okay. So we're going to start off with a bunch of, sort of trying to make some regular sort of standard definitions that we can sort of all get on board. I've put all the links to basically, the different Wikipedia pages so you can dive in deeper if you want to on anything that's actually new. Here, data storage. Hopefully, I think everyone has a good grasp for that. It's just the process of recording information on a storage medium, right? It doesn't really matter what the medium is and how you do it. It's just a way of how do we organize and transmit information on a physical medium is typically how it's defined. So, and you can do that many different ways over history. Today, in high performance computing, sort of the two in the upper right corner are the most common sort of storage devices that we have for recording digital information. Sort of, and we'll talk about what those are a bit later. Now, we all also sort of have a innate sort of understanding of what a computer file is. But the thing that I think might be new is really understanding what a file is on a Linux or file system today. And I like this definition from the Wikipedia page, that it really does highlight that a computer file is, however you think about it, it really is a system resource. It is something, it's not just the size of the file, there's other things that make up what a file is and how the operating system interacts with the data that's in the file and things like that. Of course, you're probably familiar with many, files have different formats for different types of data, and how, different applications will, be able to read certain formats. And but the one thing that if you start actually learning a little bit about sort of how Linux works and how these operating systems are organized, there's this concept of that everything is a file, and this is sort of how Unix-like operating systems are organized. There's many types of sort of files and what they do, but there, a good Wikipedia link to click on is this everything is a file concept to explain a bit more, but it really is true if you really start digging into the details. Now, a file system, right? So what is a file system? So it is sort of the software that provides an operating system with the ability to create, organize, manage access to, files on these storage devices, the storage medium that we use on these systems, right? And all file systems will have, I think, what you would, naturally assume that, some standard operations, like how to, create a new file, change the permissions of who has access to those files, how to open a file, how to read the data from the file, write data to the file, delete the file from the file system, or, close a file so the application, that was looking at the file no longer, tells the operating system, I no longer need to look at it, right? And so that's, hopefully that's pretty intuitive. The picture on the left is where it gets complicated, and we'll get to that. But the types of file systems that you'll interact with on HPC systems are typically what we call POSIX based file systems. So POSIX is sort of just a set of standards of making sort of operating systems portable. But if you see that term thrown around, at least in my own experience, it's most commonly thrown around when you're talking about file systems. So just because there's a whole zoo of them and what they do. Now, when you start working on a Linux or Unix-like operating system, right, there's something called also the File System Hierarchy Standard, FHS, right? So this isn't what we would call a file system, but it's probably what you have in your mind of what the Unix or Linux file system is, right? But it's not. It's actually just a set of conventions used to organize the directories and files you'll find on any computing system that is using different file systems in sort of Linux world, right? And so you'll see a lot of, the cartoon on the left, you can take a look at that later and compare it to, I did a quick list of at least that first top row, the root directory with the different directories and things. And so you'll see things that match up, but you'll see other things that are new. And so every system is sort of unique, but there are standard sort of directories and things and files that you'll find on any operating system that will sort of use the FHS to organize things. But for the most part, on any Linux system that you work on, whether it's sort of a laptop, desktop, or supercomputer, really at the end of the day, most of the time, all you care about is your /home directory, right? Because this is where your personal sort of space resides within the operating system and on a file system, right? And so I wanted to highlight home here because this is sort of, and I put $home because that's an environment variable that always points to where your home directory is located, right? This is your personal user space where you're always on any system going to have a home directory, right? And, usually this is where you're going to want to install software, create your batch job scripts to submit to the scheduler to run on an HPC system. And it's always I forgot to mention, it's always like the first sort of working directory when you log in, right? You're in your home directory. And so this is sort of where you organize. This is where you get on a new HPC system. This is probably where you're going to start, installing software and maybe transferring a little bit of data, input files and things like that. But a few things, so usually the home directory is pretty limited in terms of storage space on any system. We, I think, have a 100 gigabyte roughly limit in your home directory by default. Different HPC centers or systems will have different policies on how much how much storage they give you there. And I put this italicized note about the total number of sort of read and write operations can also be limited, and that may make more sense later. Because usually your home directory is living on a certain type of file system, which I'll talk about in a bit. And it's just because of the nature of that file system's architecture and the type of how those are usually architected behind the scenes. There's a limit to sort of how fast you can read and write data there, because it's really sort of intended just to be sort of a little bit of storage, put a few things that you don't need a lot of read and write sort of throughput and latency constraints. And we'll talk about that in a second. So so that obviously, since this home directory and whatever file system it's living on, there's going to be other file systems on any HPC system where you have to put your larger input files or write larger output data, whatever you're doing, right? And so if you have that type of problem, right, you're probably not going to put your, 2 terabyte data set, or, if you're doing someone's, like there's AlphaFold is a big popular thing in sort of the, um, biology community these days, and has like a, multi-terabyte database that's not going to live in your home directory, right? So you have to think about, this is how you start thinking about what your problem is and where you're going to go. But you'll always usually start with your home directory. And so it comes down to sort of where we start dividing the file system world. Okay. So there are many different types of these POSIX file systems, and everyone has its own limitations, advantages, features, and things. But those, understanding what those file systems are a little bit, and what those features are, will help you determine like how and where you want to store the data, the type of data you have, and how long you want to leave it there on that file system. Actually, there is a time constraint as well sometimes. Many file systems on HPC systems, will have purge policies, right? So if you have an allocation, at the end of the allocation, might be the policy of the center to sort of, hey, you need to move your data off our system because we need to make space for the next users. And that's what we call like a purge policy, right? So there really is sort of this how, where sort of type of data and time constraint on any file system. But the thing that's really new to most novice HPC users is understanding that there are 2 general classes of file systems that you're going to interact with on an HPC system. And that's a local file system, which is what you're more familiar with, say, working on your personal computer, right? All the files are sort of on the hard drive in your laptop or in the desktop. And so other computers don't have access to that data, right? It's really like the files in your operating system, your personal photos or whatever, in case of doing science, your data sets and things that you store on your local personal computer. That is sort of what you have a sort of natural understanding of, and feel for how fast that should operate, and things like that. Whereas a lot of the file systems that you see when you get into your home directory and can start playing with, including the home directory, are what we call distributed file systems, where the data that you're interacting with, say in your home directory or some of these other file systems, are actually not located on the computer that you're sort of currently interacting with, right? That computer is calling out over the network to that storage system, and that the file system that lives on that storage system, to get access to your files and interact with your files, write to them, read to them, or read them, delete them. All of those sort of file system interactions are happening over a network and across, as I sort of show in this little cartoon in the bottom, is actually interacting not at sort of an individual device layer like most local file systems are, but you're interacting with multiple servers and different types of servers just to carry out that sort of same set of operations, right? And so hopefully that gives you a sense of like, oh, distributed file systems are going to sort of probably not act as quickly and with the low latency as a local file system, right? Because your computer that's right next to your sort of hard drive in your laptop, or your processor, right, has very direct access to that data. Whereas anything in a distributed file system, there's a whole other set of CPUs and network switches and other things that are involved, right? And so this is where things get sort of different when you start using an HPC system. Now, I like to just put this quick tool up here. This DF tool is a standard sort of command line tool that will just give you information about the file systems on any Linux operating system that you're working on. And so this is just a quick output of sort of the top 20 entries of when I go into and log into Expanse, our sort of main production supercomputer right now for NSF at SDSC, and look at the what file systems are available. And so this tool just lists the type of file systems, which we'll talk about here in a bit, the how much space is available, how much has been used, sort of the paths of where they're located on the system. And yeah, you can see there's a lot kind of going on, especially if you just look down the type column, right? So there's a whole bunch of different file systems, right? And some are local, some are distributed, right? And that's sort of the divide, right? I think on the next page, yeah, of course, some of these file systems are usually explained, what's available also in the user guide of any HPC system. So that's sort of on this note, because the first question is, okay, so you have all these file systems, you have your home directory that's on a file system, you have these other file systems that maybe you have to put larger sets of data or use in a different way than your home directory. But the first question always comes up is like, okay, well, how much space do I have, right? This is what we call a quota usually, right? And that sort of limits the amount of space in a reasonable way for all the users that are sharing the different file systems, right? The problem is it's not universal how you look up how much space you have. There are some file systems that have their own sort of command line tools, and I think I show one later. But also some HPC centers have their own like command line tools that they've developed to sort of help dig out that information for you. So the best place to start is actually in the user guide and check the storage section. It'll tell you about the file systems. I mean, you'll see what with the df command, what file systems are there, but in the user guide, they'll explain like how they want you to use it, maybe what your typical quota is or how to look it up. That's sort of where I would go. But there is another command that's, will help you sort of at least check how much space you're using. It's also useful to know if you haven't used it before. This is the du command. And there's other options and things, but usually you use it with the -h option to make it sort of human readable, so it's not just in bytes, I think usually. But so for example, on Expanse, this is usually if we see a user is running out of space, they're getting some errors. They send us an email like they're having some errors, their jobs are failing. Sometimes it's because they've exceeded their quota on their home directory, right? So they need to start thinking about, okay, where do I actually need to put my data from my job, or and so you'll get these errors, and so this is what we do to check how much space you're using. It can take a long time to run depending on sort of how many files and things you want, but this is sort of the most basic command that you can use on almost any system to figure out how much data do I actually have in a directory, right? It doesn't really matter about the file system. It's looking at more the directory level, like how much data do I have here, right? You can use it on any directory, but here I'm just showing how I would use it to check how much space am I using in my home directory. Okay. So hopefully that gives you a little bit of sense of what a file system is. So I want to sort of switch back to, a little bit of information about data storage devices and systems, because these are the things that the file system is actually sort of managing your data on, right? And there's reasons why different file systems will be architected with different types of devices for different reasons, right? And it all really comes down to, at the end of the day, we're always shuttling data between different types of storage devices for different reasons at different times, because the speed of different devices and the sort of the response time or latency of these different storage devices are depend on where they're located relative to the CPU. And so that sort of determines how fast the different things in this, what we call the memory hierarchy, how fast your data can be accessed by the computational, the units on the processors, right? And so at the end of the day, if you've thought about like, how sort of data from your application gets shuttled into cache on CPUs. At the end of the day, it's not really any different than thinking about going the other direction and thinking about, okay, it's coming off the local hard drive, and maybe then there's a network distributed file system that I'm accessing data from. And the the higher you go up closer to the CPU, faster the access, but smaller usually the storage, the capacity that it can hold. Whereas the larger, slower storage systems uh, are where you sort of keep your data long term, and where everybody puts their data because it's cheaper storage. We have these large storage systems, and it's more reliable. The reliability is greater there to save your data. You know. Okay. Just quickly, I think probably most people hopefully have a sense of what, when we talk about memory, we're usually talking about the sort of CPU memory, or maybe if you're using a GPU, there's sort of GPU memory, but it's really after moving off of the processors, the CPU and the CPUs themselves, right? This is the next closest storage device in that hierarchy, right? And um, the memory that's available on HPC systems are a little bit different than usually your commercial sort of personal computer memory. The principles are the same, but they sort of have this error correction, which makes them more reliable. There's always sort of, in most HPC systems these days, there's usually two processor units. You can kind of see here in the picture here, the cross like gray boxes. Those are the heat sinks for the processors, and in between you can see the memory banks where these memory modules will live, right? And where the next closest sort of data storage is to the CPU. And so it gets a little bit more complicated because there's really, kind of two banks of memory. Like there's sort of, one set of those cards is sort of dedicated to the CPU on the left, where the other set is dedicated to CPU on the right. And so actually moving data around in like what CPU and what memory actually physically matters too at the end of the day. But yeah, sort of a different talk for that. Um, but a quick command I wanted to throw up here, if you're just curious. So the free command I use it a lot just to check out what's going on and how much sort of memory is being used by a system at any given time. If you haven't used it before, it's a quick way to check, how much memory is available on any given system you're on. But of course, remember, many HPC systems have different node types and will have different amounts of memory available. And there's other devices like I mentioned GPUs that have different memory. Free is just looking at sort of the traditional CPU memory that's available on the system, that is being consumed by the operating system, maybe your application, maybe other people's application if you're on like a shared compute node. And also, I think I make a note here, if you're running a job on a node, the free amount of memory isn't necessarily what you've asked for and being allowed to use for your job, sort of separate, right? So if you look closely at these screenshots, you'll see sort of I'm asking for different amounts of memory, but what's being shown by the free command is very different. So, okay. And this is sort of also where the just some terminology that if you haven't really heard it before, there's sort of what we call volatile and non-volatile memory. It really breaks down into sort of where that sort of memory hierarchy uh, splits, right? Where everything from sort of the main memory, the memory modules we were just looking at, to the caches and registers that are on the actual processors. This is what we call volatile memory, right? And so any data that's stored in those devices require that the system's powered on, right? The electricity has to be, the lights have to be on for this sort of what we call usually primary storage, right? For your data and applications and things that are running on the system. Whereas the non-volatile or non-volatile storage is probably how I would usually refer to it, is sort of the data storage devices that you use to store data after power is removed. It's like good. You have a good feel for this. If you turn off your laptop, it'll start up again. Look at your hard drive the next day. You turn it back on, and everything's there, right? This is the just a set of terminology that if you're not familiar with, you might see it out there, right? Now, I just wanted to give you a quick overview of some of the devices that are sort of backing the file systems, and give you a sense of just why they're still used and where and what the limitations are, right? So, for a long time, hard disk drives, so HDDs, you'll see mentioned different places, are these sort of really electromechanical devices that, have these spinning disks that you would write to this sort of magnetic storage domains that would store, the bits of any file that you're writing to the system, right? And so it's the file system and the device drivers. These are what are working in combination to represent your files from the file system in physical reality on these devices, right? And so you can imagine, so today, these aren't really used for like local storage, say in your personal computer. Same, I would say, in any HPC system you're probably working on today. Any compute node you're on is probably not using these hard disk drives anymore, right? Because they're sort of, these mechanical things that have spinning disks. You can imagine the rate of how fast they can spin determines how fast you can read and write data to them. And they're mechanical, so they break easier than, say, everything that's just an electric circuit, which is next. But they are cheaper and have really high densities per dollar, that you'll still find them as components in many of the distributed file systems that you might interact with, right? And so the performance of those file systems are actually still limited by the mechanics of how these things work, right? But it's sort of how it is. Now, the more common sort of main sort of secondary storage after memory for you on your personal computer and most of the compute nodes on an HPC system that you interact with, like for the local file systems, right, are what we call solid state drives. And so it's basically, the technology that removed all the mechanical parts for hard drives, right? And so you'll see referred to SSDs, right? And so there's different formats and sizes, but at the end of the day, the key thing is there's no moving parts anymore, right? And so there's different types of physical limitations, but they're more reliable. They're getting cheaper every day, over time. And this is sort of, this is where the operating system on any compute node that you might be interacting with probably lives. And the next most important use case for you specifically is most HPC compute nodes these days have a local sort of scratch disk where one of these SSDs are that you can use. So if you run out of memory, the next place is if you need to read and write data to a local file system while your job is running, there is usually one of these scratch disks. It might be something other than located at /scratch. That's a pretty common one, which we use. But yeah, just to be aware that this is something that might be, available on any node that you work on. And it's going to be my advice to always try to use this first before any other file system, as your job is running. So, but you'll also see some file systems on HPC systems these days there's increasingly sort of these multi-tier file systems that you might interact with, and they use these faster solid state drives as sort of a buffer in sort of the first tier of a distributed file system, where you write all your data or read, the most active data out of, these NVMe solid state drives, right? And then once the data sort of becomes cold, it gets pushed back to the older, maybe spinning disk part of the tier, or secondary tier or something like that. Anyway, but there's also still one more that you might see out there if you're working on a certain system. So there is still sort of magnetic tape. really spinning uh, um, tape drives that will, write to magnetic plastic film. It's still actually widely used because it's really cheap and pretty reliable for mostly use it for archival and backup cases, right? So it's really hard to, I mean, it's really easy to sort of write data out for backup to a tape drive, to a tape system, and stick it in the system. But when you want to get it out, you have to sort of retrieve it, and takes, getting the data back out takes longer, right? That's why it's usually more for archival and backup use cases, because they actually have to read the whole tape and find where your data is on an individual tape. Anyway, but so in the NSF sort of access world, right, there is a tape backup system called Ranch at TAC. So if you're curious about that, check that out. I've never used it actually myself, but I probably should at some point. Okay, let me just check my time. Okay, I got 20 minutes left. Okay. Whew. Still too much information here. Okay, so how do we bring what we've talked about together into hopefully this aha moment of sort of where the limitations are going to arise in any given file system, and we'll talk a little bit about where they do in some examples here. Okay, so coming back to this idea of the POSIX file system, so you have a good feel for you know opening a file, creating a file, reading data from a file, maybe. It's pretty natural for I think most of us. But there are sort of these more fundamental elements of these file systems that are called inodes and data blocks, essentially, right? And this is sort of how you know files and directories are sort of constructed on any of these POSIX sort of file systems, and they play a key role. And hopefully, that's hopefully the aha moment of the end of the next couple slides. But just to sort of set the stage, I don't have any good, get a lot of good time to find some good figures and things to explain this stuff. But essentially, a block, you hear the term block, it's really uh, uh, a sequence of bytes that is being written to one of those storage devices, right? There is a physical block size at some point, but it gets a little murky because, right, there is a physical block size on the device, but the file systems and the operating systems also set sort of the block sizes that they manage, right? And so you might see there's two sides of the coin. There's sort of a physical block, and there's also sort of the logical block from the software side, right, in the operating system. But at the end of the day, just think about it as a sequence of byte that's part of usually a file, right? But this is at the low level of how these file systems think, right, about your data, right? And usually on most of these file systems, the block size is 4 kilobytes, you'll see. And so you can kind of, have good examples yet of showing how you can easily show this and check this and things. But so there is sort of this assumed chunk size of your files, which can become important when you're reading and writing files, right? So if you're reading and writing things that are less than 4 kilobytes, right, you're sort of that extra space in the block, it's still always read, right? You always have to read that other stuff that doesn't matter. And so hopefully your data is bigger than, or your files are bigger than 4 kilobytes. But if they're not, definitely start thinking about how maybe you can organize your data a bit better. But yeah, so a few other things about blocks. Yeah, so the bytes in a block are sequential, so they're always sorted together, both logically and sort of on the physical medium, right? But where they are on the physical medium within a file, they could be all over the place, right? And so there used to be this thing back in the day called defragmenting your hard drive. So this was trying to reorganize the blocks, so the blocks for every file was closer to each other, so it'd be easier to read, right? But yeah, okay. So but yeah, so the underlying storage systems are sort of organizing blocks, and ideally sort of the logical blocks from the file system are aligned in sort of running in parallel sort of with what the storage system thinks the blocks are and how they're organized, right? That's sort of this two sides of the coin of what a block is. Now, the big thing, the new thing that usually people don't know about when they're first starting out and thinking about file system. I mean, I only learned really about these a few years ago when I started working in the group here, is what an inode is. And so an inode is is just a data structure in the file system that describes the different objects in the file systems, like files and directories, right? So the inode is really the thing that stores the metadata about your file or your directories that you might see in your home directory, right? There's this thing called an inode that exists on whatever file system you're in, whether it's a local file system or a distributed file system. There is a concept of an inode that is tracking where your data is, where your files are, where your directories are, right? And so you can imagine anytime you want access to a file or open a directory, what's happening on any file system, the operating system's going to find the inode first, right? Because it doesn't know where your data is. The inode does, right? And so so this is why metadata operations on any file system is sort of, if you don't understand why that's important, hopefully you do now, right? And I'll show you some data here by the end of the talk. Now, the directory is different than a file, different than an inode in these file systems. It's the thing that contains a reference to the files or other directories on the file system, right? And so, it has information about the names of the entries, sort of the names of your directories or your files, and the inodes that are sort of associated with them. So it's sort of every directory is sort of the database that has an idea of where to of the names of your files and directories and the inodes that are associated with those files, right? It's where it sort of joins the two things together, right? Yeah, the primary key, if you're familiar with databases a bit. Okay. And so in this concept of, blocks, inodes, directories, a file is just a set of blocks, right? It's stored in the file system. And you could argue that files don't actually have a name, right? Because the name of the file is actually stored in the directory, in the data structure itself, right? So it's really the directories and the inodes are where the operating system looks to get your data blocks back, right? And so there's all these, again, so hopefully it gives you a sense that there's all these other objects that are really floating around that you don't usually think about that are helping you access the data in your file, right? And looking up those other objects in any file system, right, has different performance consequences. But yeah, again, sort of come back to everything as a file. And there's different types of files. It gets a little bit more complicated, but the basic idea is sort of how this all relates to one another. And so I put this, okay, about a little over 10 minutes left. I put this up as I mentioned earlier that, there's sometimes different file systems have like their own command line tools that you can look up your quotas and check your usage and things like that. I mentioned a bunch of other things that here I'm not going to get into with this Lustre file system, which we'll talk about briefly here in a second. But I wanted to show you here, this is, there's a very clear example here of, okay, so if you look, let me just go to the next example. I put two up here, so I have sort of two accounts on Expanse here. So you look to the sort of the left side of both of these quota commands. So one, I'm looking up the, sort of what my statistics are on this Expanse Lustre Scratch file system and what my usage is there as a user. The next command is sort of looking at what our overall group is in our sort of project storage location. And what you can see here is a few things, right? So you can see sort of the limit, like what is your quota limit of storage on these file systems in these different locations. How much is being used, right? And that's usually what you care about, right? Like how much storage do I have? How much am I using? But if you look to the right, there's something maybe new, right? It's the files and the quota and the limit. Uh, those are the inodes, right? Because every file system, there's a in addition to a maximum amount of storage space, there's a maximum number of inodes you can have. And so we actually limit here. You can see in the Scratch file system, the Lustre Scratch, everyone should have usually by default a limit of 2 million files, right? So if you have 2 million files, you need to think about a little bit more of how to organize that data when you're dumping it onto our Expanse Lustre Scratch file system. This might be true on other file systems, right? You can see at below in the group project storage, the limit set to 0, which basically means there is no limit, right? But this is like a very clear example of like that's inode. So I'm using, I guess, 6 in my test account. I don't really use it too much, but if that could be a problem for you on any file system, right? That if there's a limit of how many files and directories you can have, you need to start thinking about that, right? And it's really because of the inodes. Okay, 10 minutes left. Oof. Okay. So I want to do a quick overview of a few common file systems and sort of try to bring it together where the sort of terminology and concepts you've learned so far, relate to what we're going to see here with the performance of these different file systems. And so I'm just using Expanse again as a sort of our canonical example. It's pretty straightforward. HPC system has a bunch of nodes. Every node has sort of the node local scratch I mentioned, but your home directory lives on what's called an NFS server. We have, I just mentioned here, the Lustre file system. We also have what's called a Ceph file system. And how you use these and what they're used for on the system. I'm just kind of give you a rundown here. Let's skip this one. But coming back to this original df command to sort of check what types of file systems now. So we're going to sort of run through what some of these are, right? And so this ext4 file system is sort of your default, usually file system that's the local file system for, say, your operating system. You can also see there's a slash scratch directory, right? Or the slash temp, if you're familiar with using slash temp, right? And you can see the availability. So usually, like on our systems, like these local file systems, right? Some people still use the temp directory, unfortunately, because ours is very tiny. And so you run out of space very quickly. You're supposed to use the local scratch because that's a whole separate disk. The slash temp is really for the operating system that lives on a different disk. So again, this is why these different file systems and directories exist, different devices. But this is like one of the most common local file systems you'll see if you run this command. The next one is your first distributed file system, but this is the most common one used for home directories on HPC systems, I think, right? This is the network file system. And so this is a nice cartoon, that shows sort of the architecture of an NFS system where your application or your commands that you're running, say, on the login node or on a compute node, right, are really going through this layer of software and then eventually going out over the network and making a call to another physical server that has physical storage devices that are sort of organized by the file system and then retrieving your data or writing your data. So there's this whole process that's happening from communicating between servers and client nodes in the system, right? And so this is why you can hopefully get a sense that if this is why things are slower when you interact with a distributed file system. And this is like the most common, the first one you'll probably interact with when you log into any HPC system, because it's usually what your home directory is coming out of. Right? Okay, so you can see here on Expanse, NFS, NFS, NFS. We have multiple NFS servers. So you might see this as well on any HPC system. Every user is usually on a single NFS server, so you're on a particular one. If someone's behaving badly on your home directory server, you might see things slow down, and we'll get contacted by people like, why is my responsiveness of my home directory not as good as it was yesterday? Like maybe someone else is doing something that's affecting it. Maybe they're doing too many metadata operations or to your file system, whereas maybe someone else in your research group also has an account on Expanse, but maybe they have a different home directory and they're not seeing a problem, right? So these are the complications that arise with these distributed file systems and sort of the debugging as well. That this is really where other people can affect your sort of daily work routine and sort of how fast even your jobs will run, depending on how your jobs are interacting with your home directory or the other file systems. Lustre. So I mentioned Lustre already. I'm not going to go into the details, but and this is sort of the idea for the next talk in the series is to talk about parallel file systems and parallel I/O. But Lustre is what we call a parallel distributed file system, and it's used to write sort of large blocks of data from many thousands of sort of clients and can write large amounts of data very quickly, depending on how everything's organized. And so this is sort of, allows you to write sort of from many different sort of compute nodes to a single file in sort of something called, if it's like an MPI code, there's MPIO. It's kind of beyond the scope of this talk, but it's really designed for, say, like doing a weather simulation and dumping out sort of every so often the state of the world in that weather simulation, right? And it's in one large file, that one snapshot, right? Or a few files, right? It was not designed for heavy, large amounts of metadata operations, right? Reading and writing too many small files too quickly, too often is sort of the most common thing that you'll see be the biggest problem at most HPC centers. It's the most common thing you'll get an email about, like, oh, the Lustre file system's down. It's probably because someone abused it and was doing too many small files too quickly. And the reason for that is there's a very, so you can look at this diagram later. There's a link to sort of exploring sort of Lustre, but what you can see here quickly in the diagram is you can see that there's actually metadata servers, right? And so Lustre, these file systems can figure out how to implement directories and inodes and things however they want to change the performance. But so Lustre, right, it has metadata servers. So that's sort of a bottleneck in the system. So if you're doing lots of reads and writes, you're pounding these usually limited number of metadata servers where there's many other sort of these object storage servers where the data in your file actually lives, right? The inodes basically live on the metadata servers, right? When you're interacting with the system. So if everybody's going through this sort of metadata bottleneck and you're the one being the most abusive, you might get an email from us at some point, or any HPC center. Anyway, so hope that makes sense. So you can see here again, just there's our Lustre file systems. In our case, if you look closely, it's only one file system. We just sort of segment part of the file system into sort of scratch space for temporary things and project space for sort of longer term storage. And this comes back to the issue I mentioned early on about policies, right? So the scratch directory in our Expanse Lustre file system, right, is purged regularly, right? So after, I think, what is it, 90 days, after a file is created, we delete it, right? And so this is, you have to start thinking about policies, too, like where do I put what data and when do I move it from, say, the scratch part of the Lustre file system to your project storage, or we also have Ceph if you need another file system. I think we're running at the top of the hour. So I think I'm going to skip over Ceph. Check it out. It's probably one of the more common file systems that you'll see on new HPC systems these days. We have if you look in the df command for expanse, we have a few different Ceph file systems and what they're used for. But Ceph is kind of interesting. It's more of a platform. Like you can have block file like storage, but there's also object storage, which I haven't had a chance to talk to you about today. So you can configure it many different ways in how it's configured at any given HPC center for a given system will depend. We sort of have both the block file type file system for Ceph and access, and with the sort of the POSIX type file system, and this sort of newer object-based storage stuff. Okay, and you can read here why later, well, why it's useful. Yeah, so there's a Ceph file system if you need that. And you'll see there's a host of other file systems out there, I would say, in sort of the in the Silicon Valley world. There's a lot of companies trying to come up with better storage and or storage systems to sort of sell to the enterprise customer, especially the AI folks these days. And this is why. So let's wrap this up really quickly. Give me maybe 5 more minutes max. So this is a study that I did last year, basically, of this very simple benchmark, and that we used this sort of ImageNet data set to do sort of as one of our standard testings for new GPUs over the years. And when using TensorFlow, one of the deep learning frameworks, right? The benchmark would usually traditionally had been to take the data sets, which is sort of 1.2 million JPEGs, which are all pretty small, actually, like maybe 100 kilobytes on average. And you'd want to take that 1.2 million JPEGs and transform it into these TF record files before doing the training of the model. And so this benchmark here is just that process of doing the transformation of sort of 1.2 million JPEGs into a couple hundred, maybe 128, 256 TF record files that are more manageable and sort of optimized to do the training on the data in this sort of new representation, right? And what I did is I did that conversion. This pre-processed image in it is really just take these 1.2 million, create these TF record files. And I did it on the different file systems that we have, right? And so you can see here the runtime, right? It's the same exact code. It's only changing where are those 1.2 million files and where does the output, the smaller TF record files go in this sort of workflow. So you see here on the left, you have the node local scratch disk, right? So this is on all of our compute nodes. And in this case, like we have like 1 terabyte, so I could fit the data set into the node local scratch on any given compute node, because it's only 150 gigabytes total or something like that, right? So it's not a huge data set in size, but in number of files is where the problem is, right? You can see here I did it on our home directory server. It's like, okay, almost 10 times slower because it's going out over NFS, right? And so it's not a local file system anymore, but it's going out over the network. There's all these other servers involved. You see that it didn't fall over, right? And so I did this on the Expanse Lustre file system, and you can see here some of the worst cases are almost 100 times slower doing the same process, right? And so why is because these are really small files. There's lots of them. It's what I told you not to do on a Lustre file system, right? I did it to show you why you don't even want to think about doing it, right? If you're going to put, say, this data set on the Lustre file system, you want to leave it packaged up in like a tarball that's compressed, and only uncompress that data on the local scratch and work with it there, right? This is why you don't want to uncompress 1 million files on a Lustre file system, right? Because if you're just going to read directly from there, it's going to be bad performance while the job is running. It's also just going to be painful to navigate around those directories because every time you run an ls command, it's looking up a million inodes to figure out where the files are, right? So this is how hopefully the concepts are coming back together, like why you see different performance and how you should structure your data on these different file systems. And again, I put stuff here, and we were doing some file system testing, so I won't even comment on the other two. But I put a link to, if you really want to curious, like what that script was that did this test, you can kind of, I put it um, in our GitHub for now, because eventually we're hoping as part of Complex to also develop some sort of take-home examples and things that you can run yourself. This one is way too complex. Obviously, you're not going to spend hundreds of hours running this test, but it'll give you a sense of like, what shuttling data around between different file systems and for different reasons, looks like, right, in practice, at least with that quick example. Okay. I'm gonna just kind of leave this here and we can go to Q&A. Hopefully some of these just recommendations and best practices will make sense now that you understand what an inode is and sort of how these, what's a local file system versus a distributed file system. But if they don't make sense, feel free to reach out and the one thing I will say at the very last one is, please back up your important data to your own storage, because most HPC centers don't have backups, right? Things like Lustre, right? It's petabytes of, storage servers. We don't have sort of twice the money to pay for the backup on the other one, right? So if you don't have a backup strategy, please do figure out where your backup file system is, where you're going to keep your data long term. Okay, so I'll just quickly to wrap before questions. So I put these two links here on additional information because the data management and file systems on Expanse was given by my boss and our CTO, or yeah, CTO, a couple of years ago. And so it's a little bit different flavor of maybe more direct and practical, like, hey, this is how you should use the file systems on Expanse. Where Complex, we're trying to sort of generalize things a bit more. So if you really want very specific details, this is kind of the last talk that we have on our website and YouTube, I think. And the slides are there so you can get that. And then when I was doing research, trying to figure out like how to start, thinking about what we can do different, I really found the using the NIH HPC storage systems talk and slides pretty useful. You might, now that you've come to this talk, understand a little bit more what they're getting at in that set of slides. So I put those there because kind of the two that I'm trying to mash together in some more generic way. All right, thanks everybody.